I appreciate Jeff calling attention to the Beetle Award. I should mention the steel bridge area really cleaned up at NASCC. John O'Quinn from High Steel is going to be recognized with a Lifetime Achievement Award. Dominic Coletti will be recognized with the Lifetime Achievement Award. We claim them as Texans. Dominic got his master's, I think, at UT Arlington. John was headed up Hirschfeld for obviously many years. And then we also have Ronnie Medlock is going to be recognized with the Higgins Lectureship Award, which is one of the highest awards that AISC gives. And you probably will see Ronnie very nervous around April as he tries to put that together. And then Carl Frank also is being recognized with the Jerry Heyer Award, which is the top award given to educators. So Texas cleared up. Ronnie, we still claim you as a Texan as well. So anyway, so I appreciate the opportunity to kind of talk a little about some of our research that we've got going on. Got a lot of slides, so I'm going to go through them kind of quickly, talking really mainly about 3 studies that we have ongoing. The first one is focusing on some bracing behavior. Then we'll talk about some work we're doing on ancillary structures, about weld repair, and then also we're doing some work on the Triple-Girder cap, which is a nice lead-in to everything that's going on today. And really want to commend David. This is an outstanding program today. I really kind of excited about a lot of it. Unfortunately, I've got to miss the rest of the morning because the university expects me to teach. They just don't have their priorities straight. But anyway, so, okay, to talk a little bit, I'm going to talk first about some recent studies and ongoing studies we've got on stability bracing provisions. I really want to call out David Fish as well as Aiden, who's down here in the front, who've been heavily involved in both of these studies. And when we start to look at this, the upcoming 10th edition has got stability bracing provisions in it. And some of that may be new to some of you, but it's work that's been around for a very long time. When we start talking about what we have to design for stability bracing, we find out that the stiffness is a function of 3 different components, okay? The stiffness of our brace itself, like the cross frame, the in-plane stiffness, as well as cross-sectional distortion. And it's governed by the equations for springs in series, okay? Which when you look at this, the total system stiffness is smaller than the smallest of the individual components. Okay? So areas we've been working on a lot in the last few years are actually the stiffness of cross frames themselves, as well as the in-plane stiffness that we've got going on. We used to think we really knew what the in-plane or the brace stiffness was, and we did a study sponsored by TxDOT about maybe, I said 7 or 8 years ago, I think, and we found out actually we don't know what we're doing very much there, and we incorporated this thing we call an R factor that accounts for eccentric connections when we're using WTs or single angle type members. But generally, these stiffness equations work pretty well. The R factors that we have, we've kind of recommended values of a 35% reduction in the stiffness during construction. And then when we're evaluating fatigue and so on, we have about a 25% reduction. Those are things that have been in AASHTO in Chapter 4 for some time. We are refining them a little bit. Another thing that we've been doing is we've been working on this study with David and Aiden is understanding a lot more about the efficiency of some of these systems. And it was a very detailed study we ended up doing. We're recognizing cases that, a lot of times we go in, we've got a certain stiffness of a cross frame. So I've got like the stiffness with a single cross frame. Essentially what I have is a half a brace per girder. If I add another brace, another girder line, then I've got 2 braces. And what happens is I essentially go to 2/3 of a brace per girder. And then if I go back and I add another one, I get, 3/4 of a brace per girder. If I get lots of girders, I go to 1 brace per girder. So what happens is we're going to end up seeing that the CNC term here accounts for the improved efficiency of our different cross frame lines as we're adding some of those additional braces. So in the current edition of AASHTO, when I say current, I'm assuming the 10th edition is sometime going to come out, which it should be later this fall, we're hoping. But we've got a term in there for beta G, which is the in-plane stiffness of our girders. And we discovered this back in the 1990s, and we came up with an equation. And when we derived that expression, we did it for really a single cross frame at mid-span, and it was really for a twin girder system, and then we expanded it to multiple girders. And what that did is it recognized, first of all, that the in-plane stiffness of the girders really impact our behavior. What we're finding more recently is it can become unconservative in some cases as we get more bracing lines along the length. And this is where David started doing some work when he came back and worked on his master's and really got some nice expressions that we ended up coming up with. Now, I want to say, don't worry about the 10th edition provisions. They are conservative. They work well, but we're going to be improving the behavior, we think, quite significantly in the 11th edition, which beyond about 55 years or something with the rate we're going right now. So in any event, kind of looking at what we did in order to come up with this, it was a very detailed study. It was a complicated study because we have to kind of isolate cross-frame stiffness from the end plane stiffness. And what David did is he ended up looking a lot at the end plane stiffness effects through like the system mode of buckling, and came up with some really nice solutions that we think for those expressions. So many of you are probably aware back in 2008 or so, we ended up discovering the end-plane stiffness mode, and we had to go and tell all the bridges that this is a potential mode. We don't understand why we discovered this all of a sudden, and all of a sudden all these bridges started coming up with these problems. But this was the equation that we had derived back in 2008, and it was derived for a twin girder system. What David kind of went in and did is kind of expanded on this, and we've got some new terms in there that allow you to go where they have 2 girders, 3 girders, or 10 girders, very accurately predicting the system buckling mode for our systems there. Now, in looking at that, we can end up getting this, and we think it'll actually have a very significant improvement on what we can end up doing from a design perspective. But the other thing that we end up doing on this is kind of coming in and recognizing that the in-plane stiffness is closely tied to the system buckling mode. So what David kind of went and did is he derived this new equation that's shown right here that actually has a lot more applicability to a wide range of problems, and it's relatively accurate. So it's got the same things that we have like the alpha X here that takes into account like the warping stiffness of your girder system. We also, if you end up adding things like top flange lateral truss panels near the ends of your section, you can incorporate this little K factor that we've got over here and kind of use an effective length factor that we can end up doing, and it really captures the behavior much more accurately on our systems. Did some very significant parametric studies. This is what Aiden was kind of working on and doing the FEA studies on this. Lots and lots of systems, different girders, different numbers of girders, different geometries and so on of our system to really evaluate the accuracy of these provisions. And this kind of shows a little bit, if I look at the stiffness that we end up getting on the vertical axis normalized by what we call the ideal stiffness versus the geometry, W over L of my bridge, the width of my bridge, the overall length of my bridge, you end up seeing the equation we have from 1993, it doesn't do a very good job. It looks like somebody took a shotgun and just kind of shot at a target there. Whereas the newer equation does a much, much better job. So very significant improvements in the accuracy that's coming from that expression. Okay. Another study, I should say, we also are working then on those lateral trusses and so on. And we're not going to have you calculate a K, but say if you're using like a couple panels of a lateral truss, you can design with a K factor of 0.7 or 0.75, something in there. That is a huge help because it's essentially on a term that's cubed. So if you all of a sudden use 0.7, you're looking at a very substantial improvement in your behavior. And that 0.7 is in the denominator, so it's a big help for our overall stiffness of our system. Okay. Another study that actually finished last spring, but we're continuing to work on it. TxDOT found a few issues that we had on our behavior. Aiden's been really going through that, so I've got his name highlighted lately and doing a lot of work really to try to refine our refined recommendations and so on lean-on bracing. I think we're all somewhat aware of the behavior of lean-on systems. We've used them in a few Texas bridges. I think I saw Michelle Ramage around here. She did some of her work on her master's back about 20 years ago. And we implemented this in a design that she had done up in Lubbock on 3 different bridges and really had some very good behavior on that. NSBA now has a new design guide on this that's out, kind of recommendations, and we're now refining our original behavior. So kind of looking at some of the things we're studying, lots and lots of finite element analyses, parametric studies, looking at the wide range of systems that we end up having. The goal is to provide essentially detailed recommendations to a designer so they don't have to be an expert in stability bracing to apply this material. So we're kind of going through a lot of this and looking at it. We're looking at cases where you have normal layouts or normal supports. TxDOT did that with a couple of bridges. Jamie Ferris was the design engineer for that. And when you get to normal supports, actually the layout that you use becomes a little bit more something you need to kind of understand the behavior on. So we're looking at a lot of different recommendations, for systems with normal supports. If I have a choice between putting 2 cross frames over here versus spreading them out, you spread them out. It does a much better job on the overall behavior of the system. Looking at different layouts, we're kind of recommending like no fully lean-on girders. And then also at mid-span of the girders, we're always saying put a full line of cross frames. And what that does is it engages the girders much less. No, this is not a timer or what's going on. It kind of is going on its own here. But anyway, those are some of the basic recommendations. And again, with these systems, we're looking at some of the contributions of top flange lateral trusses that you might put near the ends of our section. Okay. We are getting some additional, obviously, factors that come into play on here. And, David and Aiden, I keep on telling them we're going to have to start wearing body armor if we make these things too complicated. Engineers getting frustrated with it here. So, but we do think we're getting a lot more accurate, and we'll have a lot more, things that engineers can actually see and very readily design with some of the lean-on principles and get very accurate and efficient systems. Okay. Also working on this is a big improvement over what we did 20-some years ago, is the in-plane stiffness that we end up having. And a lot of this is building off of the new value of beta G we're putting in here. What we're recommending is a modification factor we call CLO that compares what we do with lean-on bracing to conventional bracing, and essentially getting a much better estimate than of the in-plane stiffness effects when we have lean-on layouts. So a lot of advances we think to coming to that. And again, what we're also then going to be doing is trying to recommend specific layouts so the designer can go in and see what's the best layout that we should actually try to have on our systems, going from cases where I have normal supports to skewed supports, and what the recommended layout are as a function of the geometry of our systems. Okay. Another thing, and I think I may have shown this last time, but I just want to kind of emphasize this. A lot of times we'll have designers come in and you've got this heavily skewed system, and they'll put cross frames in here. Don't put this cross frame right in his framing into a support on a heavily skewed system. And you don't have to call that lean on. That's just good engineering, okay? This is a really difficult cross frame to get in. If you leave it out, it actually has no impact on the stability of the system. So we're recommending in this, you can reduce up to 10% of your cross frames in a given span, and you don't have to do anything different than what you would normally do. And it just will end up with systems that are a lot easier to erect and to put those cross frames in. Okay. So another project that we have ongoing, and this is, I always kind of mention this kind of a gaudy color scheme here where we're mixing maroon with burnt orange. Okay. We've done this on a number of projects lately. Stefan is on this project leading the A&M side. But this is a study looking at ancillary structures and trying to look at crack issues that you may have with the welds. And first of all, assessing the cracks and trying to develop some potential repair techniques when we have issues where we might have problems. A lot of students working on this and postdocs. Jung Hoon is a PhD student from UT. Got Mushtaba and Aiden are postdocs working on the study. At Texas A&M, the main student is Hongil Kim, and again, Stefan is leading this as the faculty member at A&M. Doing a lot of stuff on this is, again, this is a pretty wide scope. Traffic signal structures, cantilever overhead sign structures, as well as high mass illumination poles. And specifically looking at essentially the weld between the shaft and the base plate of our section. Now, when we start looking at what we're doing on this, we found this out about 20 years ago, that this galvanizing process that we use to extend the service life of these structures, a lot of times when you do that galvanizing, you have this thick base plate with this relatively thin pole shaft. When you dip that in the galvanizing system, there's a differential expansion, and it leads to sometimes cracking in those welds. So before this even hits the field, a lot of times they have cracks in them. Lately, what you can do on these is they actually are inspected typically after that, and the welds are repaired, but we've got a lot of poles out there that might have some cracks in it. So what we want to do on this is try to go out and first assess the cracking level, and then try to go through and look at this from a behavioral perspective of when do we need to repair those welds, when do we maybe need to replace the pole, when do we just need to monitor it. And those are some of the things that we want to try to look at. We've done a lot of work, mainly on the high mass illumination pole side at UT Austin on this, done lots of fatigue studies on these systems, kind of to go and look at, induce the fatigue crack and look at the performance of them. We've done some also ultimate strength kind of tests over here. We're pushing laterally on some of those systems. We're going to be using similar test setups in this. The other thing we want to do then is come in and say, when we do have a crack, how can we repair that? So we detect the crack, and then what's the repair process that we need to use on some of those systems. So again, what this started with was first a field assessment of different cantilevers, overhead sign structures, high mass illumination poles, and traffic signal structures throughout Texas. The way we're assessing that is using phased array ultrasonic testing. We have a couple of experts on our team. Stefan's very strong with this. faculty member Salvatore Salamone at University of Texas also is very strong in this, and Jung Hoon and Hong Gil also are experts on it. I'm not so much of an expert on it. So, but what this allows us to do is kind of to get in quickly and assess and locate the cracks, and essentially look at the depth of crack and the sizes of those cracks on our pole systems. To start out this first year, we went to some of the major metropolitan areas. I call Bryan a major metropolitan area, so there we go. Around the state, and looked at poles in those areas and assessed the cracking. Okay, and in each of these different jurisdictions, we went and found 10 of each of the high mast, cantilever overhead sign structures, and traffic signal structures. So that's 120 samples. And going through and really trying to look at the geometry as well as the location of the cracks on the different systems. Try to just understand a little bit about the nature of the cracking that might come in these systems, as well as looking at our ability to look at those cracks. We're also in the process of doing laboratory experiments on all 3 different sign structures or ancillary structures that we end up having. UT is going to be doing the tests on the high mast illumination poles and the cantilever overhead sign structures. A&M is doing the tests on the traffic signal structure type systems. In UT, we're going to be having a setup very similar to what we've done in our past studies for both the cantilever overhead sign structures and the high mast illumination poles. We're in the process right now of putting those structures up. As far as like the race to the moon, A&M 1, they've actually already got a setup where they've kind of gotten it up and actually started to put some cycles on this. So what we're essentially doing is pulling up on this section, so kind of make you dizzy here. You can kind of see essentially as we're cycling this up and down, it's essentially putting, tension in the upper portion of that as we're pulling up on that pole. That can allow us to grow that crack and assess then, we're using the phased array, how well we can track that crack growth. And we'll essentially get it to a certain level of damage, then come in and evaluate different weld repair techniques for some of those systems. Okay. Where we're at on that, we've completed the field assessments. We're in the laboratory. We've got high mast illumination poles as well as traffic signal structures that we're going to be testing. We were fortunate enough to get a lot of them from the field. We also are having a traffic signals pole actually fabricated at Valmont. That should be actually done in about January or so. I will mention right here, we're probably going to have some cantilever overhead sign structure specimens fabricated. If you know of some that need to be taken down or whatever, hey, we'd love to get them. Anything we can get from the field with existing damage, as well as the geometry, we would love to have. So if you find anything in the next few months, please let us know about that. Okay. Kind of the last project I want to talk about is one that just started here at UT Austin on the Triple-Girder steel straddle cap systems. This is a nice lead in because we're talking a lot about that this afternoon. The main student on this is Baran Koyak, and we also have Aiden and Mushtaba, 2 postdocs that are also working on this study. This is a joint study with Texas Tech. Sung-Young Park, who was a postdoc here at UT a few years ago, started a position at Texas Tech, and he and Srijan is a PhD student at Texas Tech that are also working on this study. Okay. This kind of builds off, we had a project, TxDOT Project 7012, which focused on taking welded or conventional box caps and trying to come up with improved details that would show some redundancy. We actually finished this project, and we think we came up with some nice recommendations that allowed this to be a redundant system. Had very good performance in the laboratory. We did a lot of FEA work on it. The Triple-Girder now provides us another great option that's got a redundant system. So to kind of get in, we look at the behavior that we're trying to do here. I think a lot of us are aware of the Triple-Girder cap that was done up in Connecticut a few years ago. Here in Texas, we've had a lot of them designed here in Austin, San Antonio. They're seeing a lot more usage with these systems. 3-girder system is redundant, great option for what we're doing. Our goal here is to try to kind of come in and see if we can end up investigating maybe some improved detailing that may end up improving the performance and so on. We do have an industry advisory group that we're just starting to kick off with them and kind of talk. What we want to do is bounce ideas off of them so we don't end up doing something stupid and get in the end and say that can't be built or there's a better way to do it. So we're trying to get that feedback right now. So our goal is to look at the Triple-Girder systems, and like a lot of them, like the one up in Connecticut, have been done with what we call a stack geometry, where the girders are on top of the system there and essentially the load is coming directly on the top of our system there. We also want to look at cases where we might have a corbelled geometry, where the loads may be coming in on either side with a bracketed type system, as well as an integral option on this system. So looking at the different geometries that we might end up having. When we have the corbelled or even the integral continuous system, those systems you can end up getting obviously some torque that comes on your system due to differential reactions on either side of that system. So all of a sudden the torsional stiffness of this cap becomes a lot more important. So, some of those things when we look at it, when I have a closed box shape, those are ideal, right, for torsion because the torsional stiffness of a closed shape is thousands of times larger than a comparable I-shaped type section or an open shape that we end up having here. If we get to the triple I girder system, though, I'm going to call it a pseudo-open, or you could call it a pseudo-closed type system. Even though it's 3 individual girders, we tend to use batten plates and so on to kind of engage those adjacent girders, and we can end up getting it to behave a lot more like a closed system, which can really be very beneficial as we look at the torsional behavior of that. So what I'm talking about from that perspective is if I look at kind of a plan view of like a corbelled geometry where I've got, maybe a different number of girders coming in here, different span girders, but I get torsion on there. Just even looking at batten plates near the ends of the section, it kind of engages those boxes to act a lot like what we do with tub girders, right? Quasi-closed type systems. In the upcoming AASHTO, it allows you, like on straight tubs, to kind of come in and say, you don't put a top lateral truss all along the length. It's mainly the ends of the section where they're the most efficient. We think we can get kind of a similar behavior as you start getting into some of the battens and so on that tie these 3 girders together and really kind of enhance our torsional stiffness of our system. So some of the different details we're kind of looking at on here is if we move the webs out a little bit on the outside 2 girders potentially, now you have a bigger cell in there. And if that is kind of a pseudo-closed system, the torsional stiffness is a function of the area of that cell. So it can improve it potentially from a torsional behavior. I think actually it'll also improve the aesthetics, and now it starts to look more like a box type section. Okay? You don't have to move it all the way out to the edge, but anything you do there will make it a little bit more like a box section. So there's some advantages both structurally, I think even aesthetically there might be some major advantages. When we start to look at this system here, we do have to be careful with like local buckling behavior because obviously we have a bigger overhang there. Potentially you may have some local buckling that we control with like B/T ratios. Okay. So when we start to look at some other things that we've looked at potentially doing instead of using batten plates, and this way maybe where the fabricators tell us that's a dumb idea, but we want to look at that, is I got 3 girders. Maybe what we do is we make the interior girder 2-3 inches deeper and actually just overlap the flanges. Now then you could put bolts wherever you want. You don't have any batten plates. So it's just a possible option that we want to look at. There will be geometries. Maybe that doesn't work very well, but there may be geometries where it works very well and it's maybe not that difficult. We want to actually try to look at that. It gives us a lot of different bolting options as well. You don't have to put bolts at a close spacing all along the length. You're just going to engage them at various locations along the length and try to improve the local buckling behavior, but it may also kind of give us a little bit improved performance. Whenever we start a research project, we always do some background studies and try to get the students up to speed on finite element analyses. Our students have really jumped ahead on this. We've already got some 3D FEAs. We started kind of the geometry of the Connecticut 3-girder cap. Looking at the base model has 3 equal girders. We're also looking at cases where we just shift those webs outwards. And then we've got the cases where we're overlapping our sections here. Now, in design, you probably wouldn't use the same flange thicknesses, but for the purpose of comparing apples to apples, we use the same geometry for each of them just to look at the overall behavior of these systems. So kind of coming in here, starting with a case where we've got our girder systems here side by side with a stack type geometry, so there's no torsion applied to this system. We look at the behavior of using like the conventional, I say it's conventional even though it's new, the case where we've got 3 equal girders right here. We get a behavior that looks like this, and this was actually controlled. The limit here was a local buckling of the top flange of this section. Now when we move the webs outwards, okay, yeah, we didn't get as high because we had more of a local buckling problem because again, we've got this large overhang on the inside right there. Now when we use the case where we overlap the flanges, all of a sudden the plate buckling coefficient goes through the roof. So one of the nice things here is it does kind of get rid of that local buckling behavior. I shouldn't say get rid of it, it enhances it very substantially. So we think there can be some benefits to this. We've also done some studies kind of looking at cases with an eccentric load on here and looking at combined bending and torsion. And when we look at this, now we look at the behavior individually of these 3 individual girders, and they do behave a little bit differently. For example, if we look at the centered flanges right here, you kind of get these deformations where each girder kind of deforms a little bit differently, okay? As you go to like the case where we offset the webs, well, you got the same behavior in a little bit lower, local buckling performance. When we end up going to the overlap flanges, yeah, it kind of behaved more as a unit. And again, there was no local buckling, at least at the load levels that we were looking at there. So anyway, we still want to work on this, obviously. These are just preliminary analyses, but we think we'll maybe learn a lot about potential detailing that we may end up improving, and we'll try to see how that actually works. And I decided not to do a summary slide, so I wasn't talking about everything I talked about. So I don't know if there's time for a question or two, or sure. Yeah.
Straddle, when you have a single point load on a girder, do you understand how it's distributing the load to the other girders, the adjacent ones?
Oh, thanks. So the question is, how is the load distributed to the other girders? We have a point load on it. And generally what happens is it's distributed through the diaphragm. There are internal diaphragms that tie these three girders together. And that's how it tends to engage these. And one thing that kind of, is a question that's kind of come up on the three girder cap is how many bearings do I need under the ends of it? I'm of the opinion you could get by with just one on either side and it would be fine. But there's this question, actually, do I need two or do I need three? We're getting kind of crazy. We're asking questions because we can. Two is the maximum you need under each side. I think you could actually get by with one. But the question on that is, what if I fail one girder? If it doesn't have a bearing under it, how am I going to engage these systems? And so you find out once you get past the first diaphragm, even if you've fractured it, it engages all three girders. We saw that same thing when we were looking at kind of that last study, 7012, on the redundant, box sections, that you could get a failure in one of the webs on the side, and 5-6 feet away, you fully engage the cross section again. But it all happens through the internal diaphragms that are spaced along the length with access holes through them and so on. Okay. Yeah, Jason?
Yeah, maybe feeding off that, I'm aware of a major project that I'm going to share some hearsay with you about. So I'm summarizing hearsay, so don't quote me here. But this project is intended, the preliminary design right now has a mixture of stacked and integrated three-girder vent systems. And as I understand it, Federal Highway is taking the position that the stack system can be considered redundant, but the internal system has to be proven redundant. Are you guys going to be looking at redundant, like fracture scenarios with the internal system?
So the question is, are we going to, I'm saying this so the people online can hear what you said. So the question is looking at whether or not an integral or core bolt type application is redundant versus a stacked, as FHWA considers to be redundant. We're not doing like what we did on the last study where we cooled things down with nitrogen and introduced a fracture and showed that it wouldn't jump. It's a three-girder system. So we've always said that's redundant. We're going to stick with that. What we're planning on doing probably though in our specimens is actually putting a splice halfway along the length and looking at what happens when it's fully spliced, and take off the splice plates, and you can then see kind of what happens as far as engaging those additional girders. So it would show that, and we are planning on doing concentric loading, eccentric loading that would end up looking at that. So we think our test would show, yeah, that's redundant. Okay. But I have issues a little bit with this that, it seems like we can't get out of our own way. This is a redundant system. Let's stop asking or causing this. We don't do this with concrete girders. So there's no reason on this system just to get into that. It's just my opinion. But I think we'll show that. Okay. And there was a question, I think, if there's still time, I don't know.
A couple minutes. The overlapping flange concept is very interesting. Are we able to get away from sealing requirements between those flanges, though? We talked about maybe not needing bolts the whole length.
Yeah, I was Rob Connor, a professor from Purdue University, outstanding. He's been doing a lot of work on like pack rust and things like that, pack corrosion, pack out corrosion. I asked him, he doesn't think it'd be any issues whatsoever. It's no different than if you have the batten plates, in my opinion, and you've got something you potentially doesn't. These are open air in general, and that's one of the things you want to do is to keep air being able to circulate around them and so on. So I don't think it's a big issue.
I was wondering even if you introduce a spacer of some thickness, a fill plate that avoid the pack rust issue.
We'll consult with people that know more than I do about it, but I don't think it's going to be an issue. But I wouldn't put a spacer. I would just say let's not overlap the flanges if we go to something like that personally. It's getting too complicated. And then what happens is you're starting to then, impact the torsional stiffness that we think is a major advantage for it. But anyway, but those are things we want to look at and make sure that we're not doing something that someone raises a question about. But I've already started asking, is that something we're concerned about, or is it not a major issue on it? So it's a good question, so we'll see. So, yeah, Ronnie?
First, last week there was an NDE workshop on highway in DC, and there was a technology alternating burnt fuel measurement. Don't get me trying to tell you what it is, but they have an instrument that can find cracks underneath coatings very effectively. So given your research, I think it'd be great to bring Edify in, and I'm sure they would come down and show you that, and if it proves effective, it'd be a nice place to put it.
Okay.
The other piece of it, mentioned basically, we're doing rates rate in lieu of X-ray or PennDOT. It's really nice because you don't have to, first of all, you don't have to disrupt the shop. We do that continuously. It's a long time to do that at night. You're going to get results the next day. But that might be something to look at for the industry here.
Sure. No, and it's, I'm learning a lot just observing what the experts there are saying. I'm not a phased array person, so don't ask me any technical questions. So, you all right, or you want to?
So we're at 10 now. So we have an open discussion session later this afternoon. So hold any questions until
And
then.
again, I apologize. I got to head out and teach. I'll be back early this afternoon. So anyway.
Thank you, Dr. Hellwig.